So now that we can find the percent compositions of all of our elements and our compounds, let's talk about the larger scale and talk about molar mass. Now, just like atomic mass, we've talked about molar mass in the past, back in chapter 2, I believe. Okay, and we said that the molar mass of a substance is the mass in grams of 1 mole of a substance. The molar mass of an element is numerically equal to its atomic mass. So whatever we see on the periodic table, that value for mass, it can be used in units of AMUs or in grams per mole. Okay, we can interchange those units. They are exactly the same. So the molar mass of a compound is calculated in the same way that we calculate atomic mass of a compound. Except we just have to change our units. They're now going to be in grams or grams per mole instead of AMUs. Okay, so 1 mole of water is still equal to 18.02 grams, just like in our previous example where it was equal to 18.02 AMUs. So they are interchangeable. When expressing the molar mass of elements such as oxygen and hydrogen, we have to be careful to specify which form of the element we're talking about. If you recall from our previous discussion of molecules, and specifically elements that exist as molecules, we had 6 on our minds that exist as diatomics. H2, N2, O2, F2, Cl2, and Br2. They all exist in nature as diatomic molecules. So we have to be careful and specify which form of the element we need. So here's some examples here. How many moles of oxygen react with 2 moles of hydrogen to produce water? Well, here we're talking about the reactant of oxygen itself. So this would be molecular oxygen, also known as elemental oxygen. Okay, so oxygen exists predominantly as O2. Okay, that's one of our examples. But we may also mean atomic oxygen as O. So we have to consider the context to tell which form of the element we are using. So when we're talking about oxygen reacting with something, that would be molecular oxygen. It's the oxygen in the air. So it would be O2. And O2 has a molar mass of 32.0, 16 times 2, because there are 2 oxygens in molecular oxygen. How many moles of oxygen are there in 1 mole of water? Well, when we're talking about oxygen being contained in a compound, we're talking about oxygen atom. So we're only talking about 1 oxygen. We're not talking about the molecule of oxygen. So in all of our previous examples, when we've been talking about oxygen and adding it in, we've been using the molar mass of 16 because we're talking about the individual atom of oxygen. Air is approximately 21% oxygen. In that case, we're talking about elemental oxygen, because oxygen exists in our natural world as a gas in the air as elemental oxygen, O2. So we're talking about O2. And many organic compounds contain oxygen. So oxygen is then contained in a compound. Therefore, we are talking about the atom. So we have to be careful about which form of these compounds we are talking about. If you see the word elemental or molecular, we are talking about the diatomic form. If it's contained in something, like contained in a compound, then we're talking about the individual atom. Okay, so now that we can talk about our masses in both AMUs and molar mass, we can now talk about interconverting between mass, moles, and number of particles. And we've looked at this in chapter 2 when we're talking about molar mass of individual compounds or individual atoms, and we were able to convert between mass, moles, and particles using our molar mass as well as Avogadro's number. Okay, so we've done similar problems to this before. We've done this in chapter 2. So let's review this a little. Let's review how we're going to use this conversion chart in order to solve some of our problems. So let's determine the number of moles of CO2 in 10 grams of carbon dioxide. So if we're starting with a mass of carbon dioxide, here we're starting here. If I want to go to moles, in order to do that, I'm going to follow my arrow into moles. So I need to divide by my molar mass. In this case, it would be the molar mass of the compound CO2. So the number of moles of CO2 from 10 grams of carbon dioxide, we have to find the molar mass of CO2 first. So CO2 is equal to the mass of carbon, 12.01, plus 2 times the mass of oxygen. So we get 12.01 plus 2 times 16. This is 44.01 grams per mole. We are now talking about moles in grams, so we have to use molar mass units, which are grams per mole. Okay, so now that we have the molar mass of CO2, we can now take the mass in grams, 10.00 grams, and we do what our conversion chart says, which is to divide by the molar mass. I'm going to set this up so we see how our units cancel. So I'm going to put my molar mass on the bottom and 1 mole on top to show that we're still dividing the two numbers. Okay, we're taking 10 and dividing it by the molar mass, but we can easily see that grams is going to cancel in my equivalency, and I'm going to be left with units of moles. So moles are the only units left. So we take 10, divide it by 44.01, and we get that in 10 grams of CO2, there are 0.2272 moles of CO2. And I'm going to make sure to label everything with both units and with the compound that makes it up. So I also have 4 sig figs here because my original number has 4 sig figs. Okay, let's try another one. Determine the mass of 0.905 moles of sodium chloride. So let's go back to our conversion here. I'm going to erase some of these. Okay, we're starting at moles and we want to get to mass. So if I'm starting at moles, I'm going to follow my arrow to get to mass, and it tells me I need to multiply by my molar mass. Okay, so we need to find the molar mass of sodium chloride. Sodium chloride is NaCl. So this is where remembering our names and being able to turn them into formulas comes in handy. Okay, we have to know how to do that. So sodium chloride is NaCl. We can now find the molar mass of NaCl, which would be NaCl is equal to the mass of sodium, 22.99, plus the mass of chlorine, 35.45, which is 22.99 plus 35.45, oops, hold on, 0.45, there we go. So that is a molar mass of 58.44 grams. Our conversion chart told us that we had to take that 0.905 moles of NaCl and we had to multiply it by the molar mass. So let's show that. I'm going to take the 58.44 grams per 1 mole of NaCl. That should be grams per mole for my units. And you'll see that moles cancel top and bottom, and we're left with units of grams. So we're still multiplying by our molar mass, just like our conversion chart told us to. I'm just showing it in a way that shows the units canceling. So we take 0.905 and we multiply it by 58.44. and we get 52.9 grams of NaCl. Again, that has 3 significant figures because my original number has 3 significant figures. Recall our significant figure rules. Our molar masses are considered constants or having infinite number of significant figures, so we don't use them to determine how many sig figs should be in our final answer. Okay. So, what I want you to do now is try this next one. How many molecules of ethane are present in 0.334 grams of C2H6? And now we're looking for molecules. So you're going to have to use Avogadro's number at some point. So use that conversion chart. It should be in your review packet, in your lecture guide. Use that to convert between grams of C2H6, which is ethane, to molecules of ethane. If you finish that one, you could also try this next problem, how many molecules are in 9.50 grams of sulfur dioxide. Okay, I calculated my molar mass of C2H6 to be 30.08 grams per mole. So, in order to do this, we're going to want to go from grams to moles, and from moles to molecules. Okay, so to go from grams to moles, we're going to have to divide by our molar mass. If we look on our chart, that's what it tells us to do. And by doing that, we're going to be left with moles. Once we have moles, we can convert to molecules by multiplying by Avogadro's number. Remember, N sub A is Avogadro's number. Okay, so let's start. We're going to start with our mass, 0.334 grams. And we have to divide by our molar mass. So we put 30.08 grams and 1 mole on top. That way grams cancel and we're left with units of moles. So let's do that. 0.334 divided by 30.08, and we get 0.0111037. Now, because this isn't my final answer, I'm not going to round with significant figures. This is now moles. Now that I'm here at moles, I can convert to molecules by multiplying by Avogadro's number. So Avogadro's number is 6.022 times 10 to the 23rd molecules in 1 mole. Okay, 1 mole will always have 6.022 times 10 to the 23rd somethings. In this case, it's molecules. So we put moles on the bottom, so moles cancel, and we're left with molecules, which is the unit that we want to be in. So we take that number of moles, we multiply it by 6.022 times 10 to the 23. And we get 6.69 times 10 to the 21 molecules of C2H6. I have 3 significant figures because there's 3 significant figures in my original problem. Okay, so that's how we find the molecules from the mass. So let's do that again with our second problem here. We have 9.50 grams of sulfur dioxide, and we want to know how many molecules there are in that mass. So the first thing we want to do is find the molar mass of sulfur dioxide. So let's take a second and calculate that. I got mine to be 64.06 grams per mole. That's my molar mass of sulfur dioxide. Now we're going to use the same track to get from grams to molecules. We just have to use different molar mass for this problem. So we're going to start with 9.50 grams, and we're going to divide by our molar mass, 64.06 grams per 1 mole. I'm going to cancel out those grams, and we're going to take 9.5 divide it by 64.06, and we get 0.148298 moles. Again, we're not rounding for sig figs yet because this isn't our final answer. After we get to moles, we're going to multiply by Avogadro's number to get to molecules. So just like we did before, 1 mole is equal to 6.022 times 10 to the 23rd molecules. So we take this number, we multiply it by 6.022 times 10 to the 23rd, and we get 8.93 times 10 to the 22 molecules. This has 3 significant figures because there are 3 significant figures in my original problem. So that would correspond with answer number C, answer letter C. Okay. Now let's take this one step further. So this question, I want to know the number of carbon, hydrogen, and oxygen atoms in 1.50 grams of glucose. So this takes a little bit of thinking because in 1 molecule of glucose, which I'm just going to write as GLU, glucose, there are 6 atoms of carbon, there are 12 atoms of hydrogen, and 6 atoms of oxygen. So if I know how many molecules are in 1.50 grams of glucose, I can then use these as conversion factors to find the individual number of atoms of each of those elements in my sample of glucose. Okay, so the first thing that we want to do is determine the molecules of glucose, which is what we just did in our previous examples. We took our molar mass, we took our original mass, we divided it by the molar mass, we then multiplied by Avogadro's number. So let's take a second and let's do that first. Let's determine the number of molecules of glucose. We found the molar mass of glucose before, C6H12O6. This was 180.18. We have the calculation doing that previously. Okay, so we're going to start with our 1.50 grams of glucose, and we're going to divide by our molar mass, 180.18 in 1 mole. Okay, our grams will cancel, and we'll be left with moles, so 1.5 divided by 180. That gives us 0.008325 moles. We then multiply by Avogadro's number just like we did in our previous examples. And we get that in 1.5 grams of glucose there are 5.01 times 10 to the 21 molecules. So if in 5.01 times 10 to the 21 molecules of glucose, if I have 1 molecule of glucose, I know that in 1 molecule there are 6 atoms of carbon. So I can use this equivalency of 1 molecule of glucose has 6 atoms of carbon. Okay, that cancels out my units of molecules and I'm left with units of atoms. So I just take this number and I multiply it by 6, and I get that in 5.0 times 10 to the 21 molecules of glucose, there are 3.00 times 10 to the 22 atoms of carbon. There should be more atoms of carbon than there are molecules of glucose because 1 molecule of glucose is made up of 6 atoms of carbon. So there should be 6 times the amount of atoms of carbon in those molecules of glucose because atoms are smaller than the molecule. This equivalency would also work for the number of atoms of oxygen. So there would also be 3.00 times 10 to the 22 atoms of oxygen. okay, because these equivalencies are the same, 6 and 6. So let's figure out the atoms of hydrogen. We take 5.01 times 10 to the 21 molecules, and we multiply that by 12 atoms of hydrogen in 1 molecule of glucose. So we take 5.01 times 10 to the 21. We multiply that by 12 to get that there are 6.01 times 10 to the 22 atoms of hydrogen in our sample of glucose. Okay, so we can always take it one step further by using our basic equivalencies that we know about individual molecules and what those subscripts mean in their chemical formula. Okay, so what I want you to do now is try a similar problem, determine the number of water molecules and the number of hydrogen and oxygen atoms in 3.26 grams of water. So this is exactly what we did in our previous problem. We want to first find molecules of water and then use that to find the individual atoms of hydrogen and oxygen in water, remembering that our water formula is H2O. Okay, so take a second, pause the video, and try out this problem. Okay, so my molar mass of water is 18.02 grams of H2O. We saw that a couple times in our lecture today. Okay, so we're going to use our same pathway to go from grams to molecules. So we're going to take 3.26 grams of water, divide it by its molar mass, 18.02 grams, to get moles. So we take 3.26 divided by 18.02. We get our mole value, 0.18091009, and we're going to multiply that by Avogadro's number. So we multiply that by 6.022 times 10 to the 23, and we get 1.09 times 10 to the 23 molecules. And that has 3 significant figures for our 3 significant figures in our original problem. So now we can think of our equivalency in 1 molecule of water is equal, it has 2 atoms of hydrogen and 1 atom of oxygen. So we can use our number of molecules to find our number of atoms of both hydrogen and oxygen. So we take our 1.09 times 10 to the 23 molecules of H2O. We multiply that by the number of atoms of hydrogen. So there's 2 atoms of hydrogen in 1 molecule of H2O. So that cancels out our units of molecules and leaves us with units of atoms of hydrogen. So we just take that number and we multiply it by 2. So 2.18 times 10 to the 23 atoms of hydrogen. So now we know how many atoms of hydrogen we have. We can now do the same steps, but for oxygen. So we take our number of molecules of H2O And we use our equivalency that in 1 molecule of H2O, there's 1 atom of oxygen. There's no math that we have to do because we're multiplying it by 1. So there's 1.09 times 10 to the 23 atoms of oxygen. Okay, so that answers our question there.